Not all the time we are able to solve the circuits with the help of Kirchhoff's current and the voltage laws. Why so? Because these laws actually gave us multiple equations and it becomes very hard sometimes to solve these many equations. Thus, we have some more advanced tools to solve the circuits quickly. Let's start by understanding some of them. First, we'll start by understanding Thevenin's theorem. So what Thevenin did, actually he told us that for any element of an electrical circuit, or more precisely any variable element of electrical circuit, you can find an equivalent circuit with an equivalent battery and equivalent resistance attached in series to that load or external resistance. Okay, let me show you with the help of this example. Suppose we have this circuit here. So we have certain steps to start with. In order to solve according to Thevenin, what we'll do? First, we'll try to calculate RTH. What this RTH is? RTH is actually net resistance across the circuit. So I'll just dictate the points and I want you to closely hear it. So first we'll calculate the RTH. It's known as the Thevenin's resistance. Thevenin's equivalent resistance. Equivalent resistance. And after this we'll be calculating the VTH. It is known as the equivalent potential across the load resistance. Now suppose we have the load resistance this 5 ohm and we have to calculate the current in this resistance. How can we do that? Let me show you. The very first step is to find the RTH. In order to do that, we'll short the circuit from the batteries. Where we have the batteries, we'll short the circuit, and where we have the external resistance, this 5 ohm resistance, here we'll open the circuit. So what we'll see, let me show you. So we have, if I short the circuit here, we'll get this 6 ohm. Here I also short, we get this 3 ohm, and then this is my open circuit here. These are my points A and B. This is 3 ohm and this is 6 ohm. Now, we can easily calculate RTH here. So RTH, as these two are parallel, it comes out to be 6 into 3 upon 6 plus 3. So we'll get 18 upon 9, that we'll easily calculate 2 ohm. So from here we get the value of RTH so quickly, that is 2 ohm. Now the next step is to calculate the VTH. For VTH, again what we'll do, we'll try to apply the Kirchhoff's voltage law. Let's apply in both the loops one by one. So first I'll try to apply in this loop. Before moving forward, what we can do, we can actually remove this external load resistance from here and I put it there. Now we'll apply the KVL here. So we'll take again a clockwise direction, any random direction I am taking. For that, let's say we have the current I1 and it is getting divided into two currents, I2 plus I3. Now let us try to apply the KVL in the first loop, that is EFCD. So let's apply KVL in EFCD. We'll applying KVL. Okay. Now, so applying KVL, let's move C to D. We'll get a loss of 4 volt, so minus 4. We'll get a loss of 4 volt, so minus 4. We'll get a loss of 4 volt, so minus 4. And then here we'll get again the loss. Let's say the current is flowing in this direction, downward direction only. So while doing down, moving opposite to the direction of current, what we'll say? We'll say that we'll get the gain of 6i. So let's say we'll get the gain of 6i, and then again we'll get the loss of minus 6 volt, and we are moving from positive terminal to negative terminal of this battery 6 volt. So minus 6, and here again no current will flow in this loop. So only I current is flowing in this loop, as I write here 6i. Same current will go here and we are moving with the current, so we'll get the loss of 3. I'll write minus 3i. equals to 0. Let me check. Okay, the current, fine. Oh, as you can see, if we let the current in this direction, then here should be the current in this direction, and we are moving here. So we are moving actually opposite in this 3 ohm as well. So here I should put the plus sign, and if I solve, we will get 9i equals to 10, and we will get I equals to 10 by 9 ampere in the first loop. Now, we know the current, that the current flowing in this 3 ohm resistor is actually in this direction. Now, let us try to apply the KVL here. Why we are doing so? In the second loop, that is A, B, C, F, if we apply KVL, A, B, C, F, if we apply the KVL, what we'll get? We'll actually get our Thevenin, that V is nothing but VB minus VA. Now, let us try to solve it. So, let's say we move from here. So, here the potential is VB. Then we'll get in the direction of current, we get minus 3 ohm. So, VB minus 3 multiply by this current, that is 10 by 9. And then here again get the loss of 4 volts. So, minus 4 is equals to VA. So, we'll get this VA. We'll get VB minus VA is equals to 3 is 9, that is 10 by 3 plus 4. So, we'll get 4, 3, here we have 4, 3, 3, 22 by 3, VB minus VA. Now, we have the value of this VTH, this is nothing but VTH, and we have the net resistance that we have already calculated here as 2 ohm. The only thing that we are left with is to make a circuit according to Thevenin. So what he said that we'll make a circuit like this. We put a external resistance, that is RTH here. We put our external resistance between here A and B, which is nothing but how many ohms? 5 ohm resistance. So we'll put it here, 5 ohm resistance, and here we'll put the value of our VTH. This is my VTH. Now, in order to calculate the current in this 5 ohm resistance, it's very easy for us. We can easily solve it, or potential if we have to calculate across it. Now we can easily solve. We just have to apply the KVL here. So let's try to apply the KVL. Let's try to apply the KVL. So if any direction I'll apply the KVL, what I should write? I should write VTH. VTH is nothing, that is a drop of minus 22 by 3. Then the current is flowing, let's say, in this direction only. So I'll get minus loss of RTH, that is 2 into I. This is the new I, and again the loss in 5 ohms. So 5I is equals to 0. So we'll get minus 22 by 3 is equals to 5 plus 2 minus 7 plus 7I. So we'll get easily I equals to but minus 22 upon 21 amperes. This is the way how you can solve the complicated circuit using Thevenin's theorem. Apart from this, we have another theorem that is known as Norton's theorem. What will happen there? Actually, in Thevenin, if you will notice, we have made a circuit in a way that we have attached an RTH in series to VTH. VTH is the net equivalent potential and RTH is the equivalent resistance. What according to Norton we'll do, actually we'll attach or make a circuit in which we'll attach this net equivalent resistance parallel to a current source, net equivalent current source. Let me show you how. It's very similar to this only. Here also, let me remove all this first. Let's see. Here I have the same circuit and we'll try to solve it with Norton's theorem. So as I was telling you earlier, it's very similar. We'll first try to calculate R Norton. It's nothing but same, the equivalent resistance across the external resistance or load resistance. And then we'll calculate the I Norton, that is the current flowing in Norton's circuit. Now, let us try to do that. But what's the difference here actually? If you recall, in Thevenin's, what we did in Thevenin's, we have removed this equivalent or load resistance. We have removed this load resistance like this, and then we made this an open circuit. But in case of Norton, what we'll actually do, we'll actually short circuit this main circuit. Now we'll try to calculate the equivalent resistance. So while calculating the equivalent resistance, actually it comes out to be same. Short circuiting these three batteries, 6, 3. So all in all, we'll get R Norton. Similarly, like previous example, we'll get 2 ohm. Now the only thing we are left with here is to calculate the resistance or the current flowing in this loop, because this is our external source. So what is the current flowing in this loop? So for that, let us try to understand how can we do that. We'll simply let that, okay, the current flowing here is I1, it is I2, and this one is I3. So we have I1, here we have I2, here we have I3. I can then easily write here by KCL I1 equals to I2 plus I3. Now we have to calculate the I3. I3 calculation is our main motive, but to do so, first we have to calculate I1 and I2 first, then only I can calculate I3. So let's start while calculating the I1 first, or anything. Let's start with this loop. If I see this loop and apply KVL in ABCF, if I apply KVL, Kirchhoff's voltage law, what I should write? I can write, moving up the opposite direction of the I2, I'll write 3I2 as we are gaining the potential energy. Then loss of 4 volt, so minus 4, and we get equals to 0. So I2 can easily be calculated as 4 by 3 ampere. Now let's try to apply KVL in this loop, that is CDEF. So CDEF, we are applying KVL. While doing so, what we'll get? See, we'll move C to D, loss of minus 4 volt, so loss of 4 volt. Then we are letting current in this direction, I1. So in the direction of current, again loss, so minus 6 I1, and then again loss of 6 volt, so minus 6. Then moving in the direction of I2, we will get the loss again, so that is 3 ohm multiplied by I2, and that too is loss, so minus 3 ohm, and this multiplied by this I2, so I'll write directly 4 by 3 and equals to 0. From here we'll get the value of I1. Let's try to solve it out. What we'll get is 4 minus 6 I1 minus 6 minus 4. So we'll get minus 6 I1 equals to 14, and I1 will get minus 7 by 3. Now we have the value of I1, we have the value of I2. Let's try to calculate the I1. So let's try to calculate the I3 actually. So I3 is nothing but I1 minus I2. I1 we have minus 7 by 3, and I2 we have 4 by 3, minus 4 by 3. So we'll get minus 11 by 3 as I3. Now we know the I3. The only thing that we are left with is to draw the equivalent Norton circuit. So how it looks like, see, a resistance, that is the R Norton 2 ohm, parallel to the current source. So this is my current source. This is my current source with minus 11 by 3 ampere, or 11 by 3. You can directly take the magnitude as well. And then we have this load resistance here. We have this load resistance here, that is 5 ohm. Now let's say I'll again try to calculate the current in this 5 ohm resistance. How can I do that? I know the values of R Norton, I know the value of this current, and let's say the current is flowing in this direction, it is getting divided into 2, and I have to calculate the current in 5 ohm resistance. The potential across these 2 points, for the time being I'll say this point X and Y. So the potential across X and Y will remain same, means the potential across this resistor and this resistor is same. So we can calculate the I in 5 ohm is nothing but I equivalent or I Norton multiplied by R Norton divided by R Norton plus 5. I hope everyone knows that from where I get this expression. It's simple Ohm's law. Now I Norton I have 11 by 3 and R Norton I have 2 upon we have here 5 plus 2, so we'll get 22 upon 21 amperes. Then, if you recall, it's the same value that we get from the Thevenin's equation. Well, that's all for today. I hope you understood both the advanced tools that I have discussed with you all guys. Well, we'll meet again in another video and discuss some of the more advanced tools that are superpositions and nodal analysis. Till then, keep learning and keep exploring.